less than or equal to 1/100th. So
0.34.
So I have 75 over n is less than or equal to 1 over 100.
75,000.
So yeah, so this is going to be true when n is greater than or equal to 7,500.
Yeah.
Alright, so that's actually a really practical thing. If I'm doing some kind of engineering problem and I'm doing a bunch of calculations and I need to do an integral, and I just happen to know that if I'm off by a little bit, it's okay, but I can't be off by more than, I have to be accurate to at least 2 decimal places, then if I'm committed to using LRAM, then I know I'm going to need 7,500 rectangles to guarantee that, at least using this kind of estimation, to guarantee that that I have enough rectangles so that I'm not off by that much. Okay, is this all making sense basically? Hope so. All right. Next, can we do better? Can we do better than LRAM? RRAM maybe?
MRAM.
No, same. Formula for LRAM, exactly the same thing.
MRAM.
Yeah, so let's try midpoints or trapezoid. Let's do trapezoids first.
R10.
So let's talk about the trapezoid rule. And let's see, as we discussed, what kind of makes the it's all blended together. What makes the trapezoid rule bad? Where does the trapezoid rule go wrong? Yeah. No, not just when the concavity changes. Think about it. Or how about maybe an easier question first. When is the trapezoid rule perfect?
Straight lines.
Yeah, did we already say that? We already said that, right? Yeah, if you have a function which is linear, then yeah, the trapezoid rule is perfect, right? Because you just split up into trapezoids and you just estimate the function exactly. Okay, when is the trapezoid rule going to be bad? Yeah, Aniguan.
When the power is really high.
When the function's
When
really,
the function
really curvy.
interface is really, really fast, really, really fast.
Wait, wouldn't it be?
The second derivative. Yeah.
Yeah, that's exactly right, right? You're gonna have a bad trapezoid rule experience when your second derivative is very big. When your function is very concave, whatever that means. Ethan was telling it, it's like super concave when you like jumped up in the air. Yeah, if you have a function, you can kind of just make a picture of this, right? Let's take a function on some interval, and let's suppose, now how does the trapezoid rule work? Well, the trapezoid rule, you take the function at the left endpoint and the right endpoint, and you estimate that the area under the curve is like this, right? So if that's your estimate, what could the actual function look like and still go through these 2 points? What would be a terrible function that still goes through these 2 points for which the trapezoid rule would give you really bad answers? Everyone like do it with your finger. Kind of like that, right? If that were your true function, then the trapezoid rule is going to give you really bad results. So this is like bad. Whereas on the other hand, if your function looked kind of like this, so same sort of start and end points, same approximation via trapezoids. I'm looking at a particular interval now, I guess. If I have my function kind of not so concave, then it's going to be not so bad. So this is like okay. All right. So basically, the more concave the function is, then the worse the trapezoid rule is going to be. If you think about it, like if you go back to like maybe the babysitting metaphor, here, if you're checking in on them at the beginning and the end of every hour. And based on how much trouble they're getting into at the beginning and how much trouble they're getting into at the end, you assume, oh man, they must have been just getting in more and more trouble over the course of that whole hour. Let me estimate that they caused this much trouble. But if there were wild swings in like metabolism, where they were causing lots of trouble, and then they like, digested all, they metabolized all the candy, and they like relaxed, or maybe they just like fell asleep for like a little while, kind of did nothing. And then when there was like 20 minutes left before we were about to go check in on them, just like all hell broke loose, and they started just going crazy again, right? Eating just crap loads of candy and started causing tons of trouble. Then you would check back in on them, and you would assume that things had gone like this. But in fact, they would have been sleeping for like most of the time, so they caused less trouble than you thought. Does that make sense?
Yeah.
I think it makes sense. All right, so now what is relevant is the size of the second derivative. Okay, so let's suppose, just like we did before, now we're going to suppose that the size of the second derivative is less than some constant on some interval. So if we can cap the second derivative, then we can figure out how much error at most we're going to produce. Okay, and what kind of behavior will produce the most error? This is kind of a vague, this is not a vague question, this is a hard question. If I'm here, if I know I have to start here and I know I have to end here, what is going to make my estimate be off by the most? Yeah.
Maybe if there's a relative extreme out there.
Okay, it's actually simpler than that, right? If the rate at which the size of the second derivative is relevant because the faster the derivative is changing, the more it's going to be off by. And so the function which will produce the most error, Eli?
Extremely high powered odd function.
Okay, but without even getting into like what kind of function is power or whatever.
The second derivative is equal to K2.
Yes, exactly. The function that is going to produce the most possible error is the most possible error is going to result when the function's second derivative is just K2. If the second derivative, if you're telling me this is the maximum speed at which you're allowed to sort of change your derivative, then if your derivative is actually changing at exactly that speed for the entire time, and maybe think about it in terms of like an acceleration problem, right? If f is position, what's going to cause, and you say that you're allowed, suppose you have a rule, okay, so there are speed limits, right? But there are no acceleration limits. So if you want to like drive around town and you want to go as fast as possible, but you don't want to break the speed limits, you just get like a really like high-powered car. You just like accelerate. You make sure you're at the front of the stoplight, and then maybe there's just cops everywhere as far as the eye can see. And then the light turns green, and you're just like, all right, screw you cops. I know I'm only allowed to go 40 miles per hour in this zone, but I'm just gonna like accelerate from 0 to 40 in like 3 seconds just to like spite you. And then I'm going to just, as soon as I hit 40, then I'm just going to go the speed limit, right? So suppose you drove like this all the time. You're this person who were trying to get where you were going as fast as possible, but so you just accelerated as much as you possibly could, but still stayed under the speed limit. There are no acceleration laws. So, but now suppose they caught on to this and they made acceleration laws. So they said, all right, look, you're not allowed to accelerate faster than K2. Then how fast should you accelerate to gain the most possible distance? K2 the whole freaking time, right? If they're actually, imagine this is a cooler story. They abolished the speed limit laws. They just make acceleration laws. Oh, so you can go as fast as you want, but you're only allowed to accelerate at a certain speed, okay? I don't know what kind of world that would be. But, so yeah, if you wanted to gain as much possible distance, then you would accelerate as much as possible. Okay, I don't know if this makes sense. So, I guess the way to think about it is if a linear function gives you gives you a perfect trapezoid rule approximation, then the most you can deviate from a linear function is the one in which your slope is changing most rapidly. And your slope changes most rapidly when the rate of change of the slope is equal to the biggest the slope is allowed to change. Okay, so what we have here is this kind of picture. The picture looks like this. We have, this is, and what we're going to do is we're going to move everything over to, yeah, okay, I'll just draw two pictures. So here's x sub I minus 1, and here's x sub I. And this is, again, the ith subinterval. Okay, and now what I know is that when I plug it into the function f, I get this value, f of x sub I minus 1. And when I plug x sub I in, I get some other value, f of x sub I. And the trapezoid rule is going to tell you that the amount of area you got on that interval is that. All right, and what does the worst possible function look like? The function which produces the most area is going to be like a parabola. Let's call this function q. So let q be the function. Q is the function whose second derivative just is k2 the entire time. And then we're going to have a similar sort of picture, right? That's going to be, and then that is going to be like negative q of x, right? And what that tells me is that in this case, that my actual function lies somewhere in between. My actual function lies somewhere in between the most it could be off by and the least it could be off by. Is this making basic sense? Okay, so in order to figure out my maximum possible error, then I need to figure out the area of this piece. Okay, so in order to simplify this a little bit, we are going to, instead of messing around with x sub I and crap like that, we're just going to move everything over to the origin. So let's calculate. What we're going to do right now is we're going to calculate the error on the ith subinterval using the trapezoid rule. Okay. Well, and what I'm going to do is instead of I'm going to just call this h. So let delta x is just b minus a over n. For algebra reasons, let's just call that h. And so I have my function, it looks like this. All right, so the worst, and now I'm going to draw the worst possible function, which is q. That's q of x. And this y value, this is h of 0, or sorry, this is f of 0, and it's also q of 0, because, right, the approximating function has to go through the same start and end points. And then that is f of h is also q of h. Okay. And what I want to calculate is this area here. Well, there's one thing I know about this q function. That is that its second derivative is k2. So if its second derivative is k2, then we can figure out what this function looks like. What is q prime then? k2x plus c. And what's q? 1/2 k2x squared plus cx plus d. Okay, so q is some function which looks like that, right? All right, and now what I want to do is I want to figure out what this green is. So to figure out what this green is, I want to find the area under this q function. So I'm going to take the integral from 0 to h of q. So let's do that. Is the integral from 0 to h of 1/2 k2x squared plus cx plus d. Okay, so integrate that function. What do you get? Evaluated at 0 and h, right? fast. Are we okay?
Is that the end? Yeah.
Oh, dx, yep, oops. Okay, and now I plug in the h, and I get, finally, k2 over 6 h cubed plus ch squared over 2 plus dh. And what does that expression represent?
The worst error.
It's the error, no, it's not error yet. It's just the area under, it's the blue area, basically.
Yeah.
Right? It's the blue, it's the blue. Okay, now let's compute the black area, the area of that trapezoid. What is the area of that trapezoid? Well, it's q of 0 plus q of h over 2 times h, right?
Yeah.
Okay, and then what is q of 0? It is f of 0, but actually we can just compute it directly, like plug it into the q.
D.
It's just d. And then what's q of h? Plug that in also. That's going to be 1/2 k2 h squared plus ch plus d, right? All over 2 times h. You guys basically staying with me? Okay, and now, so let's just simplify this if we can. What do we get? We get 2d over 2, so that's just a d
Times h.
times h, so I can write that as dh, plus 1/4 k2h cubed plus ch squared.
Over 2.
I think I worked in, oh no, yeah, over 2. So I calculated the area under the black trapezoid, I calculated the blue area, and therefore the green area is like the difference between the two, right? So can we just subtract these two boxes? What do you get? What happens? Most things cancel, right? If you get k2 over 6 h cubed plus k2 over 4 h cubed. No, minus. Which is, what's 1/6 minus 1/4?
Negative 112.
Yes.
Those
Negative 112
h cubed.
k2h cubed. Okay, and this, if you're still following this, this represents, what does it represent?
That is the error.
The error on a single subinterval, right? This is the error on a single subinterval. So now to get the total area,
Multiply by n.
I multiply by
Yeah. And
n. Yeah, I multiply by n. So my actual answer is, I'm going to just drop the negative because error is a positive quantity. So this is k2 over 12. H was just our temporary substitute to make our algebra prettier for b minus a over n. And this is cubed and times n. Okay. So after doing this whole calculation, what I end up with is a formula for the errors that you get from using the trapezoid rule. And here is the formula. If you're taking some, if I is some integral from a to b of some function, then the difference between the true area under the curve and t sub n, the area is approximated by n rectangles, is guaranteed to be less than or equal to k2 over 12 times b minus a cubed over n squared, where k2 is a maximum on the on the size of the second derivative. So if I wanted to do this same problem, and the function was, what was that function I used? Was it 2 sine 3x? If f is 2 sine 3x, then f prime, as we said, was 6 cosine 3x, right? Right?
Yes.
And then the second derivative would be
Negative
18 sine 3x. And I picked this function because it's kind of obvious. What is a bound on the size of the second derivative? 18, right? The size of this second derivative is always less than or equal to 18, which means I should set k2 equal to 18. And so if I want to know the error, let's do t30. So if I want to know, I could compute t30 like we did last class, and then you could take the error is in using t30 is guaranteed to be, according to this formula, 18 over 12 times 25, or rather, I guess that's 125, right? Sorry, I'm talking about this same integral from 1 to 6 of 2 sine 3x, the one that we analyzed using the LRAM thing, and then over 900. So whatever that number is, it is 0.208. And so if you remember from over here, using 31 rectangles, my error it could be as much as 2.5. But using a slightly more efficient method, suddenly now my error has shrunk by a factor of 10, right? Now I can report that if you use the trapezoid rule with 30 rectangles with this function on this interval, then your answer is going to be off by at most 0.2. And then you can do these same kind of questions over here. All right, does this make sense? It's not everything I wanted to do, but it's close enough. All right, bunch of things going on over the next couple of days. One, there is a short test tomorrow. We have class tomorrow. It's an all-period day, and it is a test on anti-differentiation. Yeah, you can turn that on. Actually, no, just let it play. It is not that hard. This test on anti-differentiation. If you know what you're doing, you're good to go. I made a one-page 5-problem review sheet. If you did not get one of these last class, please grab one now. I'm putting them right here on T's desk. You should just do that. It'll take you like, I don't know, 10 minutes or something, and then you should be good to go. The answer key to the Wallops anti-differentiation package is up on Endline, as is the one that we were doing mostly in class together, so I think you should maybe take a minute and check your answers for that. That's tomorrow. You can get 100 on this test. This is the easiest test of the year, so just try to get 100 on it, because it's pretty easy. Then we have a couple other things going on. This is, we have a test next week. So everyone should grab one. Actually, what did I pass out? What did I pass out last class? Did I pass out like one of everything?
Yeah.
There are 3 things. Everybody take one of all of these 3. You're doing already.
We have Alex thinking I'll get the third thing.
Oh yeah, we didn't get the.
We only got 2 things.
Actually, no, we didn't get 2.
And while you're doing that, let's just quickly discuss what's going on next week. Next week is HSA week. Ostrander has dictated that all magnet students come to school during HSA week. If you are a freshman, then Piper has scheduled every moment of your time, and you are going to be like doing Chem R&E, crap like that. If you are a junior or senior, you'll be doing Puzzlepalooza. If you are a sophomore, you are going to be with me on Monday and Wednesday. So the first thing to understand is you have to come to school. You have to come to school. That's not me saying so, that's everybody saying so. What is going on? On Monday, you're going to show up in the auditorium, and we're going to basically chill for like an hour and a half. We're going to do some quiz retakes if you so desire. If you messed up some of the quizzes from this quarter, you can do a study hall, you can bring work, you can study for math, you can bring a chess set, you can bring Monopoly, you can do whatever you want. Then we're gonna go outside and we're gonna have like a picnic on Monday. During public school, you're gonna go to the picnic, sophomore picnic. So bring like a frisbee and like maybe some food and like nice like shoes you can run around in. Wednesday, we're having a test on integration. So that's going on. Yeah. You have to make that
Wait, you didn't collect the whole thing?
Oh, that was so bad. I was like, what? I didn't know what I was supposed to be doing. You're like,
Alright, just turn this off.